Have you ever wondered how we can apply protective coatings to various surfaces, creating unique textures and enhancing their properties? Well, film coating is the answer. Today, we'll be diving into the fascinating world of film coating. Come on, let's jump up to uncover the wonders of this incredible technique. The three prominent techniques in the field of surface engineering are thick film coatings by melting solidification, thin films coating from vapor, and thin film coatings from solution. In thick film coatings by melting solidification, it focuses on thermal spraying. Thermal spraying is a versatile coating process that involves the deposition of various materials into a surface using heat. It is used in a wide range of industries including aerospace, automotive, energy, and even at art restoration. This is the synthesis for thermal spray coating process. And we have the overview for thermal spray processes, which was categorized into three. We have combustion method, electrical method, and high pressure gas jet. Finally, we have here the different schematic diagram of the different methods of thermal spraying, which is thick film coatings by melting solidification.
Vapor deposition processes involve depositing thin layers of materials or films onto a substrate. These processes require a controlled environment within a vacuum chamber to prevent external contamination. Two main techniques for thin film coatings are physical vapor deposition and chemical vapor deposition.
The thin film is deposited on a base material called a substrate, such as glass or silicon wafers. In theory, any material can have a thin film deposited onto its surface. The substrate is essentially a foundation on which we will deposit the thin film. Designing and executing a vapor deposition process requires careful consideration of materials and equipment to ensure compatibility of the system. The substrate is then exposed to one or more vaporized sources. The presence of the vapors, along with other stimuli, will cause a thin film to deposit on the surface of the substrate.
In PVD, a source material is evaporated using methods like electric power or lasers, and the resulting vapor condenses onto the substrate, forming the thin film. This process does not involve any chemical reactions. CVD, on the other hand, uses a mixture of a source material and a volatile precursor. This mixture is injected into a chamber containing the substrate. Upon adhering to the substrate, the precursor material decomposes, leaving behind a layer of the source material. Chemical reactions occur in CVD.
In PVD, the deposition is generally more directional, meaning there is a defined path for how the molecules will deposit onto the surface. This can result in non-conformal films, meaning that the film may not contour smoothly along geometrically complex surfaces, such as trenches or rounded surfaces. By contrast, the nature of CVD processes results in multi-directional deposition, allowing for more conformal deposition along complex surfaces.
Thin film coatings from solution involve processes like sol gel and electrochemical techniques. Sol gel converts a liquid precursor into a solid gel, which is then deposited as a thin films. These coatings exhibit versatility, adhering well to various substrates such as glass, ceramics, and metals. Here is an example process of a sol gel method. electrochemical or electrodeposition is the conventional process of coating a thin layer of one metal on top of a different metal to modify its surface properties. Based on the principles of electrolysis, it is a process that uses electrical current to reduce the cations of a desired material from an electrolyte and coat those materials as a thin film onto a conductive substrate surface. Here is an example process of an electrodeposition.
As a learning scientist and a ceramic engineer in the process, we gained extensive hands-on experience working in ceramic engineering laboratories. We mastered various techniques such as ceramic powder synthesis, ceramic shaping methods, casting, pressing, extrusion, and firing processes.
We successfully carried out experiments and analyzed the results, further enhancing our understanding of ceramic materials and their properties. We actively sought out internships and industry collaborations to gain real-world experience in the field.
We work with renowned ceramic manufacturing companies, assisting in process optimization, quality control, and product development. These experiences allowed us to apply our theoretical knowledge to practical situations, strengthening our problem-solving and decision-making skills, and broadening connections along ceramic industries.